In our last series of videos, we were looking at a new operation with functions called composition. It's where we take one function and compose it with another. And the way we do that is we simply evaluate the one function at the function expression of the other function, which creates a new expression. And that expression is the expression for that composition function. And we saw that when you compose the functions, if the resulting value is just the expression x, and that happens whether you compose f with g or g with f, that those functions are what are called inverse functions. You put a value into the one function, and when you take the result of that and put it into the other function, it maps back to the original value. And we saw that in our previous series of videos. So we want to take these two functions and test them to see if they are inverse functions. If they are inverse functions, then f composed with g and g composed with f will all equal x. Remember how we compose the functions. F composed with g means we take the function f, and wherever there's an x, we replace it with the entire expression for function g. So wherever there was an x here in function f, I replaced it with the entire expression for function g. And now I can simplify that expression and see if it results in just the value x. If it does, that's halfway there to proving that these functions are inverses. Let's multiply through on the interior parentheses here. Negative 1/2 times x gives us negative 1/2 x. Minus a minus is plus, and that'll be 3/2. Now let's multiply by minus 2. Minus 2 times minus 1/2, minus a minus is plus, and 2 times 1/2 is 1. 1 times x is x. Minus, the plus is minus. The 2's will cancel, just giving me minus 3. Minus 2 times 3/2, the 2's cancel, giving me minus 3. 3 minus 3 is 0. So halfway there in proving that these functions are inverses, because f composed with g just equaled x. Now, to complete the proof, I have to show that g composed with f also equals x. And if that's true, then these two functions are inverse functions. So let's find the composition of g composed with f. So wherever there is an x in function g, I'm going to replace it with the entire expression for function f of x. So where the x was here in function g, I replaced it with the entire expression for function x, 3 minus 2x in this case. And now let's simplify. 3 minus 3 is 0, so that just gives me negative 2x. And negative 1/2 times negative 2 is positive 1. 1 times x is x. And we have demonstrated that these two functions are inverse functions. We demonstrated it by showing that f composed with g equaled x, and now g composed with f equaled x. Whenever that occurs, the functions are inverses. And mathematicians adopt a new notation for a function. When one function is the inverse of another function, rather than using a different letter, mathematicians will use the same letter. So this function is the inverse of the function f. They will use the same letter f, and then they'll put a negative 1 in a superscript position. Now, that doesn't mean that you're raising f to the negative first power. See, here's the problem. We only have so many symbols we can use, and sometimes mathematicians have to reuse symbols. So when it's a function notation, that minus 1 in the position that would normally be for an exponent means this is the inverse function. this function is the inverse of function f. So when you see f with a -1, that's really f inverse. This is the notation we use to identify that this function is the inverse of function f. And what's interesting about the functions and their inverses is in the domain and range. And I already kind of illustrated this, but want to illustrate it again. Let's suppose we're thinking of function f, and this is its domain, this is its range representation. This is a linear function, so we know its domain is all real numbers. And if we took a value, let's say the value of 1 for x, 2 times 1 is 2, 3 minus 2 is 1. Whoops, wanted a 1 there, not an x. That would then map into a range value of 1. 2 times 1 is 2, 3 minus 2 is 1. If we let x take on the value of 0, 2 times 0 is 0, 3 minus 0 is 3. An x value, a domain value of 0 for function f, maps into a range value of 3. But now look what happens if we take these values and put them into f inverse. If we take 1 and put it into the expression for f inverse, 1 minus 3 is -2. -1/2 times -2 is +1. So when I put 1 into this function, which makes this become the domain of f inverse of x. When I use these values and put them in for x, then this set becomes the domain of that function. And putting that value of 1 in for the domain maps it back to 1 here, which was in the domain of f, which is now the range of f inverse. Same way with 3. If I put in 3, 3 minus 3 is 0. -1/2 times 0 is 0. So using 3 as the domain value in the inverse function maps back to 0 in the domain of the original function. So the range of the inverse is the domain of the original function. The domain of the original function is the range of the inverse function. The range of the original function is the domain of the inverse function. And the one function undoes the other. Mapping from 1 to 1 under the function, you map from 1 back to 1 under the inverse. Mapping from 0 to 3 under the function f, you map from 3 back to 0 under the inverse function of f. If we let x be, let's let x be -4. So 2 times -4 is -8. 3 minus -8 minus a negative is plus, so 3 plus 8 is 11. So if we let x be -4 in the function f, it maps to 11. Now let's let 11 be the value that we put into the inverse function. 11 minus 3 is 8. -1/2 times 8 is -4. Under the inverse function, 11 maps back to -4. And that's the way it always works for functions and their inverses. The domain of the function is the range of the inverse. The range of the function is the domain of the inverse.